Welcome back. The image and video processing field is an exciting one for a number of reasons, one of which is the amazing diversity of both the applications that use image and video processing techniques, but also the types of images that arise and which can derive from any type of radiation. Now, when we think of images and videos, the ones that come to mind first are the ones that we can see. At any given moment, however, we see very little of the radiation around us. Of course, this is good enough for us to function fully, and we don't need necessarily Superman's X-ray vision. Our eyes, like any sensor, have a certain bandwidth and allow us to see in the so-called visible part of the EM spectrum. From an evolutionary perspective, the band of EM radiation that the human eye perceives is perhaps optimal, since the data that is used is highly reliable and abundantly available. The sun emits strongly in the visible band, and the Earth's atmosphere is also transparent in the visible wavelength. Having a limited bandwidth is also a form of data reduction. We would have been overwhelmed had we been able to sense a much broader area of frequencies in the EM spectrum. In this segment, we look at representative images from the various parts of the EM spectrum, from gamma ray images on one hand to the radio band at the other end. We also look at representative images outside the EM spectrum, such as ultrasound, electron microscopy, and computer-generated images. Regarding the dimensionality of the objects we are imaging, due to the invention of powerful telescopes and microscopes, we're able to see the atomic structure of objects and objects far away in the sky. The sizes of objects we can see now are from a few nanometers to hundreds of thousands of light years. So let's look at some fun images in this segment. One aspect of image and video processing that makes it such an exciting topic of study is the amazing diversity of applications that use image processing or image analysis techniques, as well as the diversity of image types that arise. In trying to put some order in our minds regarding the various image types, it's important to realize that the principal source of energy for images in use today is the electromagnetic energy spectrum. So we will look at examples of the types of imaging originating from the various parts of the spectrum. Some of the most exciting developments in medical imaging, for example, are the result of new sensors that record image data from previously little-known sources of radiation, such as positron emission tomography, PET, and magnetic resonance imaging, MRI, or new sensors that sense radiation in new ways, as in computer-aided tomography, CAT, where X-rays are collected from multiple angles to reconstruct a rich aggregate image. Another important source of energy includes acoustic or ultrasonic radiation. Ultrasound is a sound pressure wave with frequency greater than the upper limit of the human hearing range. Another important source of energy includes electronic in the form of electron beams used in electron microscopy. And finally, we have images that do not exist in nature, but they exist in our minds. And then with the use of computer graphics, they can be given shape and form, and they can be visualized. And we'll show some examples of all the images above, starting with the study of the images resulting from the various parts of the electromagnetic spectrum. Another possible classification of images is into reflection images, emission images, and absorption images. Reflection images sense radiation that has been reflected from the surface of objects. The radiation itself may be ambient or artificial. It can be from one source or multiple sources. The type of information that can be extracted from reflection images is primarily about object surfaces regarding their shapes, textures, color reflectivity, etc. Most of our daily experience in optical imaging through our eyes is about reflection images. Other non-visible examples include radar images, sonar images, laser images, and even some type of electron microscopy images. Emission images are even simpler, since in this case the objects that are being imaged are self-luminous. In this case, the information is primarily about the internal structure of the objects, and examples of emission images are thermal, infrared, and MRI. Finally, absorption images provide information about the internal structure of objects. In this case, the radiation passes through objects and it's partially absorbed or attenuated by the material composing the object. Examples include X-rays, transmission microscopy, and types of sonic images. Here is a picture of the electromagnetic spectrum, which is the range of all possible frequencies of electromagnetic radiation. The electromagnetic spectrum extends from below the low frequencies used for modern radio communications to gamma radiation at the short wavelength, high frequencies. It covers, therefore, wavelengths from thousands of kilometers down here to a fraction of the size of the atom at the other end. It might be hard to read all the numbers, but the scale here is logarithmic. So this is 1 hertz here. So then 10 to the first is here, the second, the third, and if you go all the way, it's 10 to the 14th up here at the gamma rays. And you can do a similar thing for the wavelength. We see here that the visible part of the spectrum is just a tiny part of the EM spectrum. And what we'll do next is just go through some representative examples when it comes to gamma rays, X-rays, ultraviolet, visible, infrared, all the way down to radio frequencies. Major uses of imaging based on gamma rays include nuclear medicine and astronomical observations. In nuclear medicine, the patient is injected with a radioactive isotope that emits gamma rays as it decays. Images are then generated from the emissions collected by gamma ray detectors. So the first image shows a complete bone scan. Images of that nature are used to locate infections or tumors. In positron emission tomography, PET, the patient is given a radioactive isotope that emits positrons as it decays. When a positron meets an electron, both are annihilated and 2 gamma rays are given off. These then are detected and a tomographic image is created using the basic principles of CT. So it's similar to X-ray CT. Another application is gamma ray radiography systems capable of scanning tracks using a radioactive source and a vertical tower of gamma detectors. This gamma camera is able to produce 1 column of an image, while the horizontal dimension of the image is produced by moving either the track or the scanning hardware. The system provides good quality images which can be used for identifying cargo, and by comparing it to a reference, anomalies can be detected. We also have instances where an image is obtained using the natural radiation of the object being imaged. This is the case, for example, of the star in the constellation of Cygnus, exploded about 15,000 years ago, generating a superheated stationary gas cloud known as the Cygnus loop. And this is what this figure C shows here. Similarly, we can observe the natural radiation of an object being imaged as here the bright spot from a reactor valve. X-rays were first observed and documented in 1895 by Roentgen, a German scientist who found them quite by accident when experimenting with vacuum tubes. A week later, he took an X-ray photograph of his wife's hand, which clearly revealed her wedding ring and her bones. Roentgen called it X to indicate that it was an unknown type of radiation, although sometimes they're called also Roentgen rays. So X-rays are among the oldest sources used for imaging. They're generated when electrons, which flow in a vacuum tube, strike a nucleus, and energy is released in the form of X-ray radiation. The best known use of X-rays is medical diagnostics, but they're also used in industry and other areas like astronomy. So here we see a chest X-ray, and here is the Cygnus loop that emits X-rays naturally. Higher energy X-rays are used for industrial inspection, and here we see the X-ray of a circuit board, which clearly is done to find possible abnormalities on the board. There are a number of applications for ultraviolet imaging, such as lithography, industrial inspection, fluorescence microscopy, lasers, biological imaging, and astronomical observations. Actually, fluorescence microscopy is one of the fastest growing areas in microscopy. Fluorescence is a phenomenon which was discovered when it was observed in the mid-1800s that the mineral fluorspar fluoresces when UV light is directed upon it. UV light is not visible, but when a photon of UV collides with an electron in an atom of a fluorescent material, it elevates the electron to a higher energy level. The excited electron relaxes to a lower level and emits light in the visible red region. Materials actually can have primary fluorescence or secondary fluorescence when they're treated with chemicals capable of fluorescing. Regarding astronomical observations, we show here an ultraviolet image of the globular cluster NCG 1851. In our daily experience, we think that what we see is what really exists around us, but in truth, our eyes record very little of the information that is available at any given moment. As with any sensor, the human eye has a limited bandwidth. The band of electromagnetic radiation that we are able to see, or the visible light, is quite small, as we can see from this chart of the electromagnetic spectrum. It is typically from 390 to 700 nanometers, and in terms of frequency, this corresponds to a band in the vicinity of 430 to 790 terahertz. At any given moment, we see very little of the available radiation around us, although this is certainly adequate to allow us to function fully. From an evolutionary perspective, the band of EM wavelengths that the human eye perceives is perhaps optimal, since the data that is used is highly reliable and abundantly available. The sun emits strongly the visible bands, and the Earth's atmosphere is also transparent in the visible wavelengths. Having a limited bandwidth, of course, is a form of data reduction. We could have been overwhelmed by the amount of data had we been able to sense a much broader range of frequencies in the EM spectrum. Imaging in the visible band outweighs by far all the others in terms of the breadth of the applications. Light microscopy is an area with a wide range of applications. We show here 3 images obtained by a light microscope, and you see a cholesterol magnified 40 times, a microprocessor magnified 60 times, and the surface of an audio CD magnified 1750 times. Next to the visible band is the infrared band. We spoke earlier about Landsat imaging as used, for example, remote sensing in the introduction of this week's class. We show here again a 7-band Landsat image. This is the blue channel, the green and the red channel. I then have a near IR frequency band, 2 middle IR bands, and finally a thermal IR band. Each of them provides useful information about the area that is being imaged. Some of them can discriminate vegetation better, others moisture, other mineral, and so on. This picture shows an application of IR imaging. These images are part of the Nightline Lights of the World dataset, which provides a global inventory of human settlements. The image was generated by the IR imaging system mounted on a National Oceanographic and Atmospheric Administration, NOAA, and NOAA satellite. The satellite operates in the band 10 to 13.4 micrometers and has the unique capability to observe faint sources of visible near IR emissions present on the Earth's surface, including cities, towns, villages, fires, and so on. So you see here the map of the United States. There are certainly dark areas around here, and then the map lights up around metropolitan areas like Chicago is over here, and New York around here, and Los Angeles here. We also see the map of Europe over here. It's also well lit up, but the whole continent of Africa is rather dark. After the IR band, we are now imaging in the microwave band. We see here an image of the Death Valley as seen from the Space Shuttle's synthetic aperture radar instrument. SAR is usually implemented by mounting on a moving platform, such as an aircraft or spacecraft in this particular case, a single beam-forming antenna from which a target scene is repeatedly illuminated with pulses of radio waves at wavelengths anywhere from a meter down to millimeters. This particular image here is clearly in false color. The surface color and intensity represent the radar reflection properties of the ground cover. The image is arranged like a map. The image pixels represent approximately rectangles on the ground. We are imaging now in the radio band. As were the case when imaging at the other end of the spectrum, imaging with gamma rays, the major applications of imaging in the radio band are in medicine and astronomy. In medicine, radio waves are used in magnetic resonance imaging. You see here an MRI image of a human spine. This technique places a patient in a powerful magnet and passes radio waves through the person's body in short pulses. Each pulse causes a corresponding pulse of radio waves to be emitted by the patient's tissues. The location from which these signals originate and their strength are determined by a computer which produces a two-dimensional picture of a section of a patient. Although imaging in the electromagnetic spectrum is dominant, there are a number of other imaging modalities that are also important, as we mentioned in the beginning of the presentation. So specifically, we'll say a few things about acoustic imaging, electron microscopy, and computer-generated imaging. So imaging using sound has applications in geological exploration, industrial applications, and medicine. So when it comes to ultrasound imaging is used in applications like manufacturing, but the best known application of this technique is in medicine, and especially in obstetrics, where the unborn babies are imaged to determine the health of their development. So the basic idea behind ultrasound imaging is that there is a probe which consists of a source and a receiver, which transmits high frequency 1 to 5 megahertz sound pulses into the body. So the sound travels into the body and hits boundaries between soft tissue, let's say, and bone. So some of the sound waves are reflected back to the probe, while some others travel further down to hit another boundary and get reflected. So these reflected waves are picked up by the probe and relayed to the computer, and the computer calculates the distance from the probe to the tissue or the organ boundary using the speed of sound. At the end, the system displays the distances and intensities of the echoes on the screen, forming a two-dimensional image. And this is the image we see here of this embryo at 12 weeks, or 14 weeks rather. Electron microscopy is an imaging modality outside the electromagnetic spectrum. Electron microscopes function the same way as optical microscopes, but now instead of light they use a beam of electrons. So a beam of electrons is produced by an electron source and they're accelerated towards the specimen. Interactions occur inside the sample, affecting the electron beam. So these interactions and effects are detected and transformed into an image, the same way that light is reflected or absorbed by objects in the scene. So with a scanning electron microscope, SEM, the electron beam scans and records the interaction of the beam with the sample and each and every location. So a complete image is formed by just raster scanning of the beam through the sample. So what we see here is an SEM image of normal circulating human blood, and we can see in this image red blood cells, this for example, as well as white blood cells. While light microscopes can reach amplifications up to a factor of 1,000, electron microscopes can reach magnifications up to a factor of 10,000 and even more. Computer graphics, it's an exciting field of research and development. It studies methods for digitally synthesizing and manipulating visual content. It addresses the various technologies used to create and manipulate images. One of their objectives is the creation of photorealistic images, and here you see an example of a really beautiful and appealing computer-generated image. Regarding the scale of the images we'll be dealing with, the invention of powerful microscopes and telescopes has opened to us the gates of nano and galactic worlds and enabled us to take images of objects that were previously too small or too big to capture. So the sizes of objects we can see now vary from a few nanometers for the AFM image shown here of silicon atoms to hundreds of thousands light years for the Andromeda galaxy shown here. So down here is the scale, here is 1 meter, and it goes all the way to 10 to the 21st here and 10 to the minus 9 here. An important point is that no matter what the scale of the image is, the processing techniques we will be developing and discussing and analyzing in this class are in principle applicable to any image independently of scale.